Today we're going to discuss the DeMorgan Laws, and it has something to do with the negation of a conjunction and the negation of a disjunction. So to start us off, let's copy this truth table, and I'd like you to complete it. But remember, the P column should be true, true, false, false. When we have two statements, we have 4 rows. And the Q column should alternate, true, false, true, false. So let's all put that in the PQ columns. Copy the truth table, complete it, and then restart the video. Okay, so let's complete the truth table. So when we negate P, we axiomized that the negation of a true statement is false. So these would be false, false, and then the negation of a false statement is true, so we just take the opposite truth value. And similarly, for not Q, it would be false, true, false, true. Okay, now we're going to form the conjunction of these two and we've noted that a conjunction is true when both of its conjuncts are true. So that only happens in the last one, when we have a T and a T. Otherwise, the conjunction's false. And now we go back to the P and Q columns, and we find that P and Q are both true in the first line, but there's a false in everywhere else. And then finally, we negate the column that we just did, and we take the opposite truth values. False, true, true, true. And this truth table shows us a very, very important result. Let's compare this column to this column. Are those two statements logically equivalent? No, their truth values do not match. So we could say that the negation of P and Q is not logically equivalent, I'll put a slash through it, the negation of P and the negation of Q. And what mathematical property does that look like? It looks like the distributive property of the negation over the conjunction. So we'll say the negation of a conjunction is not logically equivalent to the conjunction of the negations. So if we were to, of the simple statements, I should write that in. Okay, so if we were to negate a conjunction, we can't simply negate each conjunct and put and in between them. We cannot distribute the negation over the conjunction. But what is the negation of a conjunction logically equivalent to? What is that logically equivalent to? Well, let's extend the truth table. And I'd like to make it logically equivalent to the negation of the conjuncts, but and doesn't do it. And will not make it logically equivalent. What connective must we insert between the not P and the not Q so that when I look at the not P and not Q column, I will get what we have here: false, true, true, true. Let's look at these. False, false gives false. False, true gives true. True, false gives true. True, true gives true. It looks like we want more trues than falses. So it would imply that we need an or. And let's see. False or false is false. False or true is true. True or false is true. And true or true is true. Yes, the negation of a conjunction is equal to the negation of its individual simple statements, but we insert an or. These are logically equivalent. And this is called DeMorgan's Laws. Okay, so I'll write it down here. The negation of a conjunction is logically equivalent to the disjunction of the negation of the simple statements. All right, so let's take a look at why this should be true. Why does the and become an or? I'm going to use an example from the Bumby and Clutch book, Course 2, one of my favorite examples, where he shows DeMorgan's laws, and he illustrates it this way. He says, let P represent Colonel Mustard committed the crime. I'll put M. Colonel Mustard committed the crime. And let's say Miss Peacock planned it. So Q will be Miss P planned it. Okay. And suppose you're a detective and you get this message. So the introduction of the original message is P and Q. All right, so this is your message and you're a detective. And suppose this statement is true. So to make this message false, we need three conditions. Either Colonel Mustard did not commit the crime, Colonel Mustard, Colonel M did not commit the crime, okay, that would be not P. That would make the message false. Or not Q, Miss Peacock did not plan it. So it's either not P or not Q. If these are both true, so if not P is true, then P is false. So we have not P could be true or not Q could be true, which would make the original conjunction false. So that is equivalent to not P or not Q. In other words, the only way this conjunction could be true is if both are true. And to make this conjunction false, at least one of the conjuncts must be false, and that's not P or not Q. Remember, at least one implies or. So that's a way to argue it, but the truth table is the best way to prove it. Now, the next question is, what is the negation of a disjunction logically equivalent to? Well, let's take a look at a truth table. It would make sense that if this was consistent, that the answer should be the negation of the individual disjuncts, but the or would become an and. Let's make a truth table to prove or disprove this. So how would we construct the truth table? Well, again, now, to construct a truth table, we always start with the simple statements we have, and that's P and Q. If there were three simple statements, P, Q, R, we would have a P, a Q, and an R. But because there are two simple statements, we will have 4 lines in this truth table. So immediately, I could start filling this in the way I filled in the other one. True, true, false, false, and true, false, true, false. Now, we build this up slowly. Let's look at the left side. The left side has a P or a Q, so that would go first. And then we'll negate that column. Right? So we always start with the parentheses and build out. Then we look on the right side. We'll need a not P, a not Q, and then put it all together. And of course, it doesn't matter if you put the not P, the not Q first. It would make sense to put these two columns right after the P and Q. But again, as long as there's a column somewhere in the truth table. And the idea is to compare these two and see if we've got a match. So pause the video, fill this in, and let's see what we get. All right, so for a disjunction to be true, well, I should say when a disjunction's false, both are false. Otherwise, if there's a true, wrong color. Otherwise, if we have a true, we got a true. So this should be TTTF. When we negate that, we get FFFT. Now we're going to negate the P column, so that's false, false, true, true. The Q column would be false, true, false, true. And when we form the conjunction of these two, the conjunction's true only when both the conjuncts are true. Otherwise, we have false. And lo and behold, there's a match between this column and that column. So we could say that these are logically equivalent. And hence we just proved that the negation of a conjunction, the negation of a disjunction gotta get my right symbol here. Okay. Is logically equivalent to the negation of the disjuncts, but we form an and. All right, and that's the second part of DeMorgan's laws. Now, these are theorems, right? So I'm going to label them as theorems. And we also call a theorem a law. So whatever is proven is a law. So let's write DeMorgan's laws, or theorem. We used the axioms for negation, the axiom for conjunction, the axiom for a disjunction to prove that DeMorgan's laws apply. And it talks about how to negate a conjunction of two statements or a disjunction. And it says, the negation of and note that we have to put parentheses around the conjunction because we're negating it, is logically equivalent to the negation of the simple statements, but the or becomes an and. And similarly, the negation of a disjunction, and again, parentheses around the disjunction, is logically equivalent to the negation of the simple statements, but the or becomes an and. Okay, so let's look at an example. Okay. 1. Suppose the original statement is x is greater than or equal to 2, or x is less than negative 4. And we'd like to negate this. Negate this statement. Okay, now, to negate the statement, we could say it is false that x is greater than or equal to 2, or x is less than negative 4. Because the the term "it is false that" kind of negates the entire conjunction, the entire disjunction. So this is like negation of P or Q. All right, that's one way to negate it, but I'd like to use DeMorgan's laws. So how would we rewrite an equivalent statement using DeMorgan's laws? Well, we're going to negate the x greater than or equal to 2. So one way to negate it is to put a slash through it. And x is not less than -4. But we'd like to put that in words rather than just negating it that way. So x, the negation of x is greater than or equal to 2 is x is less than 2, right? That is the opposite situation. And the negation of less than is greater than or equal to -4. So we have to involve the complementary case. So this would be the best answer, I think. So from now on, when we want to negate a conjunction or a disjunction, we're going to use that third line. Okay, so let's try another one. All right, let's negate x squared equals 9 and y is prime. Now, inequalities are the tricky ones, and I did that one first. But when you have an equals or words, you could put the word not there. So the negation would be x squared is not equal to 9, so we could just put a slash through it. The and becomes an or. Y is not prime. Well, if y is not prime, another way to write it is that y is composite. But this is fine. This will do. So I'd like you to try negating these. So let's copy these problems down. Number 3 is Bob is good at Latin and Mary is good at French. And I'd like you to write down the negation of that in words. 4 is m is positive or m is equal to -1. Write the negation for that in words. 5 is Tom jogs an hour a day or he doesn't have soda with lunch. Write that negation in words. And finally, an inequality, which I think is the most complicated piece, the same type that we did on the previous page. So pause the video, copy this, negate them in your notes, and then replay. So the negation of number 3 would be Bob is now identify the simple statement. So we see the word and, so we know that becomes or. So the simple statements are to the left and to the right. So Bob is not good at Latin, or Mary is not good at French. Okay, so note the not should be there and the or. All right, and the negation for number 4 is M is not positive, right? And M does not equal -1. So that would be an easy way to negate it. Now, in number 5, Tom jogs an hour a day or he doesn't have soda with lunch. Okay, so there's the or. We know that becomes and. So we're going to negate the first part. Tom does not jog an hour a day. And now to negate doesn't becomes does. This is almost like the law of double negation, the theorem that we said, that not P is logically equivalent to P. We proved that in our very first video. So when we want to negate something that's already negative, it becomes positive. So we say, and he does have soda with lunch. And finally, the last one. And this is where we would want to replace it with the correct inequality when we negate it. So the and becomes or. So the less than becomes greater than or equal to. And the greater than or equal to becomes less than. And that would be its negation. Okay, now I believe you studied a little bit of this last year when you were doing Venn diagrams. Let's look at the next page. And these two statements of DeMorgan's laws can be proven with Venn diagrams. Let's call P and Q A and B. And the conjunction becomes the intersection. The negation becomes the complement. So I'll put a bar over it. So this is read the complement of the intersection of A and B. And we want to show that that Venn diagram is exactly the same picture as the complement of A, the complement of B, but a union. Okay, we'll do that in a minute. Similarly, in the other part of DeMorgan's laws, we have the union of two statements, but we look at its complement, and that Venn diagram is exactly equal to the complement of set A, the complement of set B, and forming the intersection. So let's try that with Venn diagrams. And this is a very nice exercise, I think. So let's make a picture of the complement of the intersection. All right, well, the intersection is in the middle, so we shade everything on the outside. So the complement of the intersection would be everything but outside of this. So let's shade that. Okay. Now let's take a look at the other side of DeMorgan's laws. We're going to make a Venn diagram for the complement of A union B. So A union B is inside circle A and inside circle B, but we're going to shade outside that region in red. So that was an easy one. Now we're going to take a look at the intersection of the complements of A and B. So first we have to shade the complement of A and the complement of B, just like we did on the left. So we're going to redo that. We're going to shade outside circle A in blue, and we're going to shade outside circle B in green. And now we have to find the overlap because we have an intersection. And we see that the overlap occurs outside that figure 8 again, where the blue and the green overlap. If you look carefully, the blue and the green overlap outside that figure 8. So that would prove this piece of DeMorgan's laws, the negation of a disjunction. And you may have done this last year with Venn diagrams, but it's good to review them. And Venn diagrams are used to prove a lot of theorems in logic, including the associative and property of the disjunction and the conjunction, or the distributive property of the conjunction over the disjunction, or the distributive property of the disjunction over the conjunction. These are alternate ways to prove laws in logic or theorems in logic. All right, let's just summarize now. So to conclude and to summarize the lesson, we've learned a new theorem called DeMorgan's Laws. And remember, it's the way to negate a conjunction and a disjunction. And in logic, according to the axioms of logic, this is logically equivalent to not P or not Q, or not P and not Q. The key is to remember that the opposite connective occurs here, except I didn't negate this. So let me do that. Okay, I wrote it twice. Oh, that's not good. So let me do that again. All right. So we've got or here. Oh, or here. And that becomes and. So the opposite connective appears. And just to make sure that we've got it, I'm going to include one last problem. And the last problem is Ted and Fred are handsome, or Sally is crazy. So this last problem has both connectives in here, and or. So we really have to be careful how to negate this. Well, the fact that this conjunction was put together with Ted and Fred are handsome, another way to write this in the longer form is to say Ted is handsome and Fred is handsome. So to negate that, we would say, okay, so let me write the negation. Ted is not handsome, or Fred is not handsome, which is the same as saying Ted or Fred are not handsome. So we would have to negate the conjunction there. And the fact that Ted and Fred were put together, there was a longer form to that conjunction. So we have to think of that. So that would be the first part of the negation. And then this one would be, and Sally is not crazy. So whenever we want a conjunction to belong to a certain piece, we do form shortcuts in the English language. So think about the longer way to write this, even though we usually don't do that. All right, that concludes our lesson on DeMorgan's Laws. I hope you had a lot of fun, and we'll continue tomorrow with another connective. Take care now and have a great day.